Picture a country where rain is basically a rumor, where dunes creep like slow waves and the ground drinks every drop before it can matter. More than 95% of the land is desert, and long dry months are the default setting. Yet cities glow at night, farms still exist, and millions of people live normal lives. The only way that happens is if water is engineered. Saudi Arabia didn't just find a hidden lake, it built a lifeline, a river made of steel. A nationwide pipeline system that begins at the Red Sea, pushes across scorching sand, and delivers fresh water deep inland, day after day, hour after hour. Here's what makes it mind-bending. Transporting water across a desert is already a challenge. But this system does something even harder first. It turns seawater into fresh water at industrial scale, then moves that water like fuel through a national network. So how do you build an invisible, steel river like this and keep it running? Let's break it open, step by step. Start with geography and demand. Saudi Arabia has more than 37 million people, and most live near the coasts, along the Red Sea and the Persian Gulf. That makes sense. Coastal zones are the most habitable. But travel inland and the landscape changes fast. Huge stretches are sparsely populated desert, with harsh heat and long distances between settlements. The country is famous for oil wealth, but nature rarely hands out every resource equally. Freshwater is the gap. Average annual rainfall can sit below 100 millimeters, and summer temperatures regularly climb beyond 45 degrees Celsius. In that environment, relying on local wells alone is risky, expensive, and often not enough. Groundwater can be deep, salty, or limited, and seasonal demand spikes don't wait for a wet year. The response was to build a national water backbone using high-strength carbon steel pipe, the same class of material used in oil and gas transport. This is heavy infrastructure, long distances, high pressures, and continuous operation. Costs reflect that reality. Pipeline construction can average around $3 million per kilometer, before you even count booster pump stations and desalination plants that can cost tens of millions each. Those pump stations matter because pushing water hundreds of kilometers means fighting friction, elevation changes, and pressure losses the entire way. Now the key question: where does the water come from? From the one supply the desert can't drain, the sea. But seawater is roughly 3.5% salt. Far too salty for drinking and too harsh for irrigation. So the system depends on desalination, removing salt so the ocean becomes usable water. Step 1 is building the pipe itself. Before a single trench is dug, the pipeline is born in a factory where the focus is strength, consistency, and speed. The pipe must survive constant internal pressure, impacts during installation, and brutal desert temperature swings. Massive rectangular steel plates are cut to exact dimensions. Then they're rolled into near-perfect cylinders, almost 2 meters in diameter, with walls around 25 millimeters thick. A multi-axis rolling machine bends the plate gradually until the edges meet and the tube takes shape. Next comes welding, a long longitudinal seam that turns a rolled shell into a pressure-holding pipe. After welding, the seam is cooled, inspected, and ground smooth to remove sharp edges and burrs. Both ends are beveled, so future field joints can fuse cleanly and seal tightly. Sections are typically more than 10 meters long enough to reduce the number of welds, but short enough to transport across long distances. Quality control is relentless. Pipes are measured for straightness, checked for surface defects, and verified for dimensional accuracy. Protective coatings are applied to slow corrosion, and markings are added for tracking and logistics. Many sections are also pressure tested, so any weakness shows up before the pipe ever leaves the yard. When you're building hundreds of kilometers of line, a small error repeated thousands of times becomes a catastrophe. Finished pipe moves to storage yards, stacked in batches and labeled like industrial inventory. Cranes and forklifts load each section onto specialized trailers, strapped down to prevent deformation in transit. Then the convoy heads into the interior, sometimes hundreds of kilometers, to the construction corridor. Out in the desert, the project turns into an outdoor assembly line. The first priority is organization. Staging yards along the root group pipes by diameter, length, and installation sequence, so crews can keep a continuous workflow instead of stopping to search for parts. Final inspections happen here: coating condition, pipe identification, and straightness. Any damaged coating is repaired before the pipe ever touches the ground. Because once buried, every repair becomes slower, harder, and far more expensive. Survey teams map the route using GPS, total stations, and terrain data. They stake the alignment on the ground in visible paint and markers. The goal is the most stable path. Avoid weak soils, shifting sand zones, and erosion-prone areas. On very long pipelines, routing accuracy is not a luxury. It's what protects the line for decades. Before trenching, the corridor is cleared and leveled so heavy machinery can move safely. Temporary access roads run parallel to the trench to carry welders, excavators, and supply trucks. Dust control and sand stabilization help visibility and worker safety, especially in gusty conditions. Then the trench is dug. Tracked excavators carve a continuous channel with precise depth and width. Soil is sorted on site. Suitable material is saved for backfill. Unsuitable soil is hauled away. Keeping consistent depth and alignment prevents pipe bending and misalignment after installation. In rugged mountain sections, mechanical excavation can hit solid rock. In those places, crews may use controlled blasting to break bedrock along the planned alignment. The objective isn't drama, it's geometry. Create enough depth and width to seat the pipe securely, while keeping the pipeline buried and protected. After excavation, the pipe doesn't sit on raw trench floor. A bedding layer of fine sand or screened soil is spread, leveled, and lightly compacted. This cushions the pipe, distributes load evenly, and reduces stress points that can damage coatings over time. In loose desert soils, that bedding layer is crucial for long-term stability. For large diameter lines, a construction corridor about 40 meters wide is prepared in advance. This space allows multiple crews to work in parallel, stringing pipe, welding, inspecting, coating, lowering in, and backfilling in a continuous flow. With the right logistics, progress can average around 1.5 kilometers per day. To keep that pace, some projects choose pipe sections around 18 meters long. Fewer sections means fewer welds, and fewer welds means fewer potential leak points. But longer sections also raise the difficulty level: heavier lifts, tighter alignment, and zero room for sloppy handling. Pipe sections are positioned in sequence along the trench line. At each joint, a hydraulic internal lineup clamp expands inside the pipe, gripping all the way around, holding both sections perfectly concentric during the root pass. That single tool can decide whether a joint becomes a lifelong seal or a future repair site. Welding is often automated or semi-automated, supported by large crews and specialized machines. High production systems can complete up to around 150 welds in a day on huge 42-inch class pipe. But speed never replaces verification. After welding, each joint is tested, commonly with automated ultrasonic inspection, to confirm there are no hidden internal defects. Once a weld passes inspection, the field joint coating team takes over. They clean the surface by abrasive blasting, then apply multi-component epoxy coatings that seal the steel. This coating must resist corrosion, abrasion, and moisture intrusion for years underground. Think of it as armor. If there's even a tiny gap, the desert will eventually find it. Only after the joint is sealed does the pipeline move to the next stage. Lowering in is a choreography of heavy machines. Side boom tractors line up along the pipe string, each lifting with padded slings to protect the coating. The pipe is suspended, advanced slowly, and lowered centimeter by centimeter into the trench. Operators coordinate to prevent twisting, bending, or scraping against trench walls. Multiple side booms work in sequence, lifting the same pipe string at different points so the weight stays balanced. If one machine moves too fast or too slow, the pipe can flex, the coating can scuff, and the joint can be stressed before it's even buried. Surveyors monitor elevation and curvature so the line settles naturally without trapped stress. Backfilling finishes the physical installation. First, fine material covers the pipe to protect the coating. Then, the excavated soil is returned in layers. Each layer is compacted to the required density to minimize future settlement. In desert environments, where wind and temperature extremes can disturb soil structure, proper compaction is what keeps the pipeline stable for the long run. A buried pipe still isn't a working waterway until it's connected to controls. Along the route, the line is divided into managed sections with valves, sensors, and checkpoints. Booster pumping stations push water forward again whenever distance and friction steal pressure. Flow meters track how much water is moving, and pressure gauges watch for abnormal drops that could signal a leak. Control systems can isolate a segment, reduce pumping, and protect the network during maintenance or emergencies. In the desert, this monitoring is essential because a small issue can grow quietly underground. So the pipeline is not just steel in a trench. It's a monitored, pressurized, and continuously managed machine stretching across the country. And at key points, storage reservoirs act as buffers, smoothing demand spikes when cities wake up and industries start. To prove the line is tight, operators hydro-test sections by filling them with water and pressurizing above operating levels, watching for drops that reveal hidden leaks. Once commissioned, the network runs like a living system. Pumps ramp up before peak demand, then ease back at night to save energy and reduce wear. Remote control rooms track temperature, pressure, and flow in real time, and smart valves can close automatically if sensors detect a sudden surge or collapse. Maintenance crews patrol access points, and periodic pigging tools can clean and inspect pipe interiors, spotting corrosion early. That preventative routine is what keeps a desert pipeline reliable. When sandstorms bury markers, drones and GPS guides keep crews aligned always. Reverse osmosis is where the magic is really engineering. Seawater is pressurized beyond its natural osmotic pressure and pushed through an ultrafine membrane. Water molecules pass. Salts and many impurities are rejected and left behind. To reach the required pressures, high-power pumps work in stages, raising pressure step by step as the flow moves through the system. By the final stage, pressure can reach around 60 bar, about 60 times atmospheric pressure, enough to separate salt from water with molecular precision. After the first pass, the water is nearly salt-free, but trace ions can remain. So it's often routed through a second RO stage with even finer membranes. That second stage can operate at lower pressure but achieve higher salt removal efficiency, stripping out remaining ions until electrical conductivity drops to extremely low levels. The result is near pure water, ready for mineral adjustment and distribution. After the membranes, the water is extremely clean, but it's not finished. Purified water can be too low in minerals and off balance in pH, so the plant adjusts chemistry into a safe range and restores minerals like calcium and magnesium. That improves taste, increases stability in pipes, and meets drinking standards. And it matters because ultra-pure water can be aggressive. Without minerals, it can pull materials from pipes and storage surfaces. So the plant finishes the water, balancing alkalinity, restoring a natural taste, and making it safer to move through the network. Finally, the product becomes distribution water. It enters storage and then the national pipeline network,